Welcome everyone, lecture number 28. In this video lecture, I will discuss some examples on Fourier sine and cosine transform. So let's start. We are given a function 1 upon 1 plus x square whose Fourier cosine transform we have to find. And we also have to find the Fourier sine transform of the function x upon 1 plus x square. Since this part is given after this question, so the solution of this question is obtained by the solution of this question. So we'll start. So by the definition of Fourier cosine transform of any function fx is defined as integral 0 to infinity fx cos px dx. Here fx is 1 upon 1 plus x square into cos px dx. We suppose this integration as I and we differentiate this with respect to p. So that we have x sine px over 1 plus x square dx. We now multiply and divide this whole by x so that we have x square in the numerator. Now add and subtract 1. Now we separate the integrals into two parts, where one part contains integration 1 plus x square sine px over x into 1 plus x square dx, and another part contains sine px over x into 1 plus x square. This cancel with this, and integral 0 to infinity sine px upon x, its value is obtained by Laplace transform, and its value comes out to be pi by 2. Plus integral 0 to infinity sine px over x into 1 plus x square. Now we again differentiate this equation. Mark this as equation number 2 and this as equation number 1. Again differentiating equation number 2 with respect to p, so that we have d2i over dp square is equal to integral 0 to infinity x cos px over x into 1 plus x square dx. ऐसा इसलिए किया है क्योंकि if you notice, if you differentiate it with respect to p, the integration that we obtain is similar to this I. So this can be replaced by I, so that we have differential equation d2i over dp square minus I is equal to 0. This is from equation number 1. If we use the notation d over dp is equal to capital D, then we have d square minus 1 I is equal to 0. So auxiliary equation of this differential equation is m square minus 1 is equal to 0. The roots are plus minus 1. So the complementary function is c1 e to the power p plus c2 e to the power minus p. Since the right hand side of this equation is 0, so particular integral will be 0. Hence the complete solution is I is equal to c1 e to the power p plus c2 e to the power minus p. Now we have to obtain the value of c1 and c2. So if we take two cases here, case number 1, we put p is equal to 0 in this equation. So if we put p is equal to 0, then we don't know what is the value of I at p is equal to 0. So we simply write this as this, and here we write c1 plus c2. And we take case number 2. We differentiate equation number 3. We'll get di over dp is equal to c1 e to the power p minus c2 e to the power minus p. Now we put p is equal to 0 here. P is equal to 0. We'll get di over dp. We don't know the value of this at p is equal to 0. So we'll simply write this like this. And in right hand side we have c1 minus c2. So we have equation number 4 and this as equation number 5. Now if you notice that from equation number 1, if I put p is equal to 0, then I'll get 1 upon 1 plus x square integral. So its integral is tan inverse x, and whose value is at infinity and limiting value of tan inverse x as x approaches to infinity is pi by 2. So the value of I at p is equal to 0 is pi by 2. So from equation number 1, I at p is equal to 0 is equal to limit x approaches to infinity tan inverse x, which is equal to pi by 2. And from this equation number 2, if I put p is equal to 0 here, then di over dp at p is equal to 0 will be minus pi by 2. So from equation number 2, di over dp at p is equal to 0 is minus pi by 2. So substituting these values, in equation number 4 and 5. So we have C1 plus C2 is equal to pi by 2, and C1 minus C2 is equal to minus pi by 2. So when you solve these two equations, we'll get the value of let me draw a straight line here. So solving we get C1 is equal to 0 and C2 is equal to pi by 2. So the solution is I is equal to pi by 2 e to the power minus p, where I was the integral 0 to infinity 1 upon 1 plus x square cos px dx. So its value is pi by 2 e to the power minus p. Now to get the value of second integral, let's differentiate both sides with respect to p. Differentiating both sides with respect to p. We get 0 to infinity minus p sine px over 1 plus x square dx is equal to minus pi by 2 e to the power minus p. That minus sign will cancel and we have, I'm sorry, it will be, because I'm differentiating with respect to p, so it will be x, not p. Yes, there is fraction minus x. Okay, so the value of integral 0 to infinity x sine px over 1 plus x square dx would be pi by 2 e to the power minus p. This is the answer. Next example is find fx if its sine transform is 1 upon p e to the power minus ap. Hence, obtain the value of Fourier sine inverse of 1 upon p. So we are given, what we are given? Find fx if its sine transform, means Fourier sine transform of function fx is given to us as 1 upon p e to the power minus ap. We have to find fx, means we have to take Fourier sine inverse of this function. By the definition of Fourier sine inverse of any function fp, which is obtained from Fourier sine transform, is defined as 2 upon pi integral 0 to infinity fsp sine px dp. So we substitute the value of the function fsp, which is 1 upon p e to the power minus ap sine px dp. Now differentiating both sides, on the left hand side we have this function. We differentiating both sides with respect to x, so that we have df over dx is equal to 2 upon pi e to the power minus ap divided by p into p cos px. आपको उसी फंक्शन के रिस्पेक्ट में डिफरेंशिएट करना है जो आपके लिए आसान हो. तो आप यहाँ देख सकते हो कि तीनों फंक्शन p के हैं, तो p के रिस्पेक्ट में तो आप डिफरेंशिएट नहीं कर सकते इसको, और ये इंटीग्रेशन विद रिस्पेक्ट टू p है, इसलिए यहाँ पर हम विद रिस्पेक्ट टू x डिफरेंशिएशन कर रहे हैं। ओके, तो वी विल गेट हियर df over dx 2 upon pi integration 0 to infinity. Now you can see p से p कैंसिल हो जाएगा, e to the power minus ap cos px. Okay, and its value when you integrate it by using the well-defined formula of e to the power minus a x cos bx, then its value will comes out to be a upon a square plus b square. I'm not showing the solution of this integration. You can do it by yourself by using this formula. I have told you it earlier also. Integration of e to the power minus ax over cos bx. I'm writing here e to the power ax cos bx dx. Its value is e to the power ax over a square plus b square, a cos bx plus b sine bx. Okay, using this formula, its value will comes out to be a upon a square plus x square. ओके, क्योंकि यहाँ पर इंटीग्रेशन विद रिस्पेक्ट टू x है, b कांस्टेंट है, यहाँ पर इंटीग्रेशन विद रिस्पेक्ट टू p है तो x कांस्टेंट है और a कांस्टेंट है, उसकी वैल्यू आएगी a अपॉन a स्क्वायर प्लस x स्क्वायर। तो ये वैल्यू हो गई 2 अपॉन पाई इंटू a अपॉन a स्क्वायर प्लस x स्क्वायर। So df is comes out to be 2a upon pi into 1 upon a square plus x square dx. We क्योंकि वेरिएबल सेपरेबल टाइप डिफरेंशियल इक्वेशन है, तो वी कैन इंटीग्रेट इट, we get f is equal to 2 upon pi, integration of this is 1 upon a tan inverse x upon a, and one that a is cancelled with this, which will be tan inverse x upon a plus some constant. So we have to find this constant. If you look at this equation, this equation, okay, then if I put 0, p is equal to, sorry, x is equal to 0. If I put x is equal to 0, I'll get 0. So f0 is 0 from equation 1. From equation 1, f0 is 0. So I'll put this value in this equation number 2. From equation number 2, f0 is equal to 2 upon pi into 0 plus a. 0 plus a. A is equal to 0 because f0 is 0. So the value of fx is 2 upon pi tan inverse x upon a. So fx was nothing but it is the Fourier sine inverse of this function. Okay, Fourier sine inverse of 1 upon p e to the power minus ap. It's 2 upon pi tan inverse x upon a. Now we have to find Fourier sine inverse of 1 upon p, which is obtained by if you put a is equal to 0 in this equation. Putting a is equal to 0 both sides, we will get Fourier sine inverse of 1 upon p is equal to 2 upon pi tan inverse infinity. So it is 2 upon pi into pi by 2, which is equal to 1. Okay. So this is how we find Fourier sine inverse of this function and hence obtain the value of this function using the result of this. So I hope you understand these two questions and the logic behind the solution, finding the solution of these questions. In my next video lecture, I will discuss some applications of these transforms. Thank you so much for watching the video, and if you like my lecture, you can press the like button and share it, and also you can subscribe my channel to get the notification of any new video on my channel. Thank you very much.